Well, we get to revisit an old friend that we did a handful of questions, well, more than a handful of questions ago, and see what is actually going on with respect to momentum and energy. So, our statement for this question wants us to repeat the problem 12.2a using the incorrect definition of momentum, where we have momentum is equal to mu, u being the ordinary velocity, but with the correct Einstein velocity addition rule. Notice that if momentum, so defined, is conserved in S, it is not conserved in S bar. Assume all motion is along the x-axis. Part B, now do the same thing using the correct definition, where we have momentum is equal to m eta, the proper velocity 4 vector. Again, the spatial coordinates, so 1, 2, and 3. Notice that if the momentum, so defined, is conserved in S, it is automatically also conserved in S bar. What must you assume about relativistic energy then? All right, sounds like a fair question to ask. Let's dive in. So, in part A, the conservation of momentum in S with ordinary velocity says that m sub a u sub a plus m sub b u sub b is equal to mc uc md ud. Okay, we saw that in 2 when we just had 2 particles hitting and 1 rubbing off. But in S bar, what we have is ma u bar a, mb u bar b, and so on and so forth. Is this accurate? Well, by the Einstein velocity addition rule, we have that back in system S, we have that MA, we're going from S with the U's, we get that UA is equal to U bar A plus V, and then plus, or divided by 1, plus U bar A V over C squared, so on and so forth. This time, because the denominators are all different, we cannot conclude that this is conserved in S bar when we transform from S to S bar. As an explicit counterexample, suppose that all masses are equal and that UA equal negative UB equal V and UC equal UD equals 0. Okay. If that's the case, this is asymmetric, or this is a symmetric, completely inelastic collision in S, and as we see in the next slide, momentum is clearly conserved, 0 equals 0, in S, of course, because we have momentum velocities canceling, and then we have 0 on the right-hand side, 0 on the left-hand side, so we're good. But in the Einstein velocity addition rules, U bar A is equal to 0, U bar B is equal to negative 2V over 1 plus V squared over C squared, and then we see that U bar C is equal to U bar D is equal to negative V. So in S bar, the incorrectly defined momentum is not conserved. The two do not equal. Wow, that makes the definitions even more stringent and explains why we have to use them. So we can get rid of all the hesitancy by just simply defining the proper velocity eta. So with that, we have ma eta a plus mb eta b plus mc eta c and md eta d. Cool. So what we actually need is the inverse Lorentz transformation, so we can get eta I, where I is a, b, c, d. So basically what we just have to do is switch from the transformed to the from the S bar to the S instead of from S to S bar. So that's why it's the inverse. And again, we see the relationship with gamma there, and instead we have eta bar I and then eta bar naught. Okay, this naught tells us that we are in the temporal domain there, where beta is equal to V over C. So we're good there. This is the general rule for it. So with this, we plug in everything except for this eta I gets plugged in for eta A, B, C, and D with this definition. So as you see, we get gamma, A naught, B naught, C naught, D naught. And again, everything has a factor of gamma, so they all cancel, highlighted in red. And let's see what we can simplify to. This being said, we can distribute the mass A terms into the A to A naught with beta, and the B's. Okay, so we do that to A, B, C, D. Cool enough. And just like last time in 2, we just factor out the beta terms from both of these, just like we did with the velocity terms. And we see that when we factor out the betas, we're left with MA, A to A naught, plus MB, A to B naught, and then C, D, the momentums that we expected, transformed of course. Beta here is MC, C naught, MD, D naught, so we're good there. And of course, if we want to say this, and we say that energy is conserved, then we need to say, but MI, A to I naught is equal to PI naught, which is equal to X, which is equal to energy I, and that's a typo, that X should actually be a C. So we have the energy divided by C is equal to the zeroth component of the momentum 4 vector. So if energy is conserved, this thing equals this thing, and we cancel, and then we say that if it's conserved in S bar, we have E bar A, E bar B equal E bar C, and E bar D, then so too is the momentum correctly defined, so we have this. If that's because the conservation of energy allows us to set these equal, cool, we like that. And if these two are equal, that cancels, so these two automatically have to be equal. So we like that. It's one